Hello again. Thank you for joining us. This is a Q&A edition of Space Nuts. My name is Andrew Dunkley. Coming up, we're going to be looking at Voyager 1 and Voyager 2. A question from Alan. Ron wants to talk about star formation, and Tom has brought up that maximum potential temperature in the universe thing again. We'll talk about all of that and more on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And here to answer them all with a massive disclaimer is Professor Fred Watson, astronomer at large. Hi, Fred.
How are you, Andrew? I'm just reading one of the questions now and thinking, I wonder what the answer to that is, just as you were saying. Yes, we can answer all the questions.
I think if we write a letter to the Astronomical Union and just sit and wait, we can answer it in a couple of weeks. Be a long episode, but it'll be worth it.
It'll be a long episode, yeah.
Worth it. Let's just get straight down to it, shall we? First question comes from Alan.
Hi, this is Alan Scahill from Medicine Hat, Alberta, Canada. My question is, can the trajectory of Voyager 1 and 2 be extrapolated to determine what galaxy, star, or planet they could come into contact with in the distant future? And what would the likely outcome be of such a contact? Could they be pulled into the orbit of any of these space structures? Thank you. Love your podcast.
Thank you, Alan. Nice to hear from you again. I remember him distinctly because of where he lives, Medicine Hat.
Medicine Hat,
yeah. But it's a question I think that we've had come up before in a different form. People wondering where they're headed and what they might run into. The answer is, well, probably not that complicated, Fred.
At the moment, I think they are. I don't think you can actually identify anything that they're heading towards because we've got blank sky in that direction. And just the disclaimer here, you never quite know what sort of perturbation they're going to have on the way by, outgassing from the spacecraft or a little bit of residual solar wind. It could alter the trajectory. But I do remember just turning the question on its head when your old friend Oumuamua was first discovered. The extrapolation backwards in time for Oumuamua put it somewhere near the star Vega, one of the brightest stars in the sky. But the disclaimer there was, we don't know when it left, and Vega would have been in a different place when it left from what we see now, because you're talking about journey times of millions of years. And I think the same is true of the two Voyagers and probably New Horizons as well. Pioneer spacecraft are also leaving the solar system. All of them, I think, are heading for regions unknown. And it's partly, as I said, because we don't know, first of all, how long is it going to take them to have an interaction with another body? And until you know that, you don't know where that other body is going to be in the first place. So it's a catch-22 situation.
We're talking flight times of potentially billions of years, aren't we?
Yeah.
So, right now we couldn't tell you, but over billions of years, so much will have changed, so much will have moved. Something might get in the way and influence them, or maybe they'll just go on forever and not hit a thing.
That's right. So, in a billion years' time, our galaxy will have rotated 5 times.
Yes.
At the distance of the sun from the galactic center. So you've got all that swirling stuff going on as well. The journey of every star around the center of the galaxy takes them on paths that aren't identical by any means. So you might very well find in a billion years you're looking at a completely different set of stars that it might run into.
Yes.
But the bottom line, though, and the answer to the final part of the question is, the likelihood is that it would wind up going into orbit around something. A direct collision is unlikely, but not impossible. but winding up in orbit around something else is perhaps the most likely outcome. And it's probably going to be a star, maybe a planet, might become the artificial moon of a planet.
Yeah, well, the Earth has picked up the odd rock, hasn't it, in recent times? So, that's a possibility, but we're not talking any time in the near future. I mean, Voyager 1 and Voyager 2 are barely out of our out of the sun's influence, let alone getting into deep interstellar space. They're only just sort of on that border zone, aren't they?
They are. That's right. Yes. Yeah.
So long way to go yet, Alan. A very long way to go, and maybe they'll never see a thing and probably go, "Geez, is it boring? Are we there yet?"
That's right. They're gone forever. They probably will go on forever. It's extraordinary.
Wish I'd brought more cassettes.
Yes. Quite.
Indeed.
Quite so. Yeah.
Let's move on to our next question. This comes from Ron. A question for you from upstate New York. I'll be in upstate New York in the latter half of next year. Ron, just in case you want to have lunch. I've seen a few posts about star formation being extinguished by the outflow of the supermassive black hole at the galactic core. The paper Star Formation Shut Down by Multi-Phase Gas Outflow in a Galaxy at a redshift of 2.45 inches, I assume that is, discusses the higher outflow, is it minutes? Discusses the higher...
No, it's neither. It's just the quote, the other quotation mark from the
it's the end of the quote.
Paper.
All right. Discusses 2.45. Discusses the higher outflow of, thank you, cool and neutral gas discovered by, should I start again? Discovered by the Webb Space Telescope. I can understand how this outflow would interrupt the stellar formation of the path of these jets, but I don't see the mechanism for this black hole to quench stellar formation across the entire galaxy. Do these jets precess and sweep across the galaxy? Hopefully, Dr. Watson can shed some light on this. Thanks for the great podcast. Always a learning experience. And he sent us a link to an article about this very thing. Thank you, Ron. Can you, just for me, dumb down his questions?
Yes. So it's basically, and I should say this is a really complex area of galactic astronomy, the astronomy of galaxies, and you've got processes. It depends on gas flows, the environment of the galaxy, whether it's surrounded by other galaxies, whether there's a black hole in the middle of it, and all of that throws into the mix as to whether you get this quenching effect of the gas flow can quench star formation, for example, and so stars don't form as rapidly. So I'm just having a look now at the Cosmos article that Ron sends us a link to, and it's so. Here's the sentence, and thank you. Who am I quoting? I think I should be quoting a press release, in which case that's all right, because I can't find an author for this article, but that's okay. I'm quoting Cosmos magazine. That's the Australian homegrown science magazine. It's long been thought that outflows from supermassive black holes can suppress star formation, but direct observational evidence for this has now been lacking. How can a black hole have an outflow in the first place? It's a fair question, given that black holes are meant to be so dense the gravitational field can prevent even light from escaping. So the best scientists, I think I'd agree with all this. Scientists aren't completely sure, and I think we are pretty sure actually, but the best theories suggest that spinning black holes have this outward flow of matter in the form of vertical jets of material. And it's all about conserving angular momentum. It's also about magnetic fields I might throw in. And it's so much of difficulty in proving that this wind is suppressing star formation is because previous studies have been limited to studying ionized gases which are warm in the black hole outflows. But the new study shows that more than 90% of the wind is made up of cool neutral gas, effectively invisible in previous research. And so I think that is the hint that the outflow rate that we're seeing, they say it's of the order of 100 times larger than what we thought it was, because this is in the outflow rate of the neutral gas, not the ionized gas that's had its electrons stripped off. And so you've got much more outflowing mass than was thought of before. And it's so what it says is, and again, I'm quoting now, who am I quoting now? Rebecca Davis from Swinburne University. Thanks, Rebecca. Welcome to Space Nuts. Rebecca says, the outflow is removing gas faster than gas is being converted into stars, indicating that the outflow is likely to have a very significant impact on the evolution of the galaxy. Our findings provide new evidence to indicate that black hole-driven outflows are able to rapidly shut off or quench, there you go, the word I use myself, star formation in massive galaxies. So I think the answer to the question is, I think basically Ron's thinking of the idea of jets of material coming from black holes, which is the way they are. But when they get to higher galactic latitudes, in other words, higher distances above or below the galactic plane, then those jets become lobes. We call them lobes. They become big bubbles of gas. And if there's 100 times more forming those outflows than we can actually see, it means those gas bubbles are big enough that they can affect the whole galaxy, or at least much of the galaxy, which is really the question that Ron's asking. And it's a great question. So, we tend to think of these jets as being focused just vertically one way and the other from the black hole, but they're really spreading out into a large blob to the north and south of the black hole, which can basically permeate the entire galaxy. So I think that's the answer to the question.
Okie dokie. Very good. Thank you, Ron. Great question. Thanks for sending it in. This is Space Nuts. Andrew Dunkley here, and Professor Fred Watson there. Left, right, up, down, not sure. Let's take a quick break from the show to tell you more about our sponsor, Incogni. And I'll give you a special URL to find out how to take advantage of their great offer for Space Nuts listeners. But first, what is Incogni all about? In short, this is a kind of insurance policy for your personal data. It's a software system that acts on your behalf to keep your personal information safe and to trawl the internet and clean up after you, so to speak. Consider this. Data is a commodity and people collect it for all sorts of reasons. Maybe to create a fake identity using your name or your address, email, phone number, whatever. Or perhaps they're trying to hack you for personal gain to get into your bank accounts. Or they just want to sell your information to one of those hacker groups who will then contact you and give you some fake story or issue that they need to solve and try to fleece you out of your money. And it happens every day. So whatever the motivation, it's real and it's happening right now. Protection is as simple as signing up with Incogni. And all you need to do is go to the special URL incogni.com/spacenuts and check it out. Right now, there's a 60% discount for Space Nuts listeners, and there are plans for individuals or the family and friends plan. You can pay monthly, or you can go with the annual plan, which brings the cost down a heck of a lot. And don't forget, of course, their 30-day money-back guarantee. Keep yourself safe online by having Incogni remove your personal information from data brokers, get you off search engines, and remove profile links to your old emails, home addresses, phone numbers, whatever's out there on you, really. This is a no-fuss, carefree way of keeping your personal data safe, and Incogni does all the work. You just have to give them the green light. So check it out at incogni.com/spacenuts. That's incogni.com/spacenuts, and rest knowing your information is safe. Now, back to the show.
3, 2, 1.
Space Nuts.
Okay, Fred, we have another audio question. This one comes from Tom.
This is Tom in Orlando, Florida. I have a question. One of the listeners was asking about absolute limit on temperature, lower temperature, and the upper limit. And Fred mentioned that the upper limit, there was none because particles can move as fast as they want to. Wouldn't the speed of light, I mean, there's a limit, an upper limit on the speed of particles with the speed of light. Wouldn't that be a limiting factor on the upper end on the temperature limit? Anyway, thanks for the great show.
All right. Thank you, Tom. We understand absolute zero being where all motion stops. Tom's suggestion is absolute max temperature is limited by the speed of light. I think that's where he was going.
Yeah, and that's exactly right. So that that would represent a maximum temperature because your particles are all traveling at the speed of light. And the reason why it's not the case is that if you continue to heat a gas, so yes, the temperature of the gas is a reflection of how fast the particles of the gas are moving. You continue to heat it, they move faster and faster, and they can approach the speed of light. But of course, the only thing that can go at the speed of light is light itself or electromagnetic radiation. Because what happens is, as you put more energy in, it's taking more and more energy to accelerate the particles, and they, what we call asymptotically, approach the speed of light. They never get to it. So you can put as much energy as you like in, and the particles will get more energetic, but they won't exceed the speed of light. And there's no stop, but you can keep on putting energy in, and they'll nudge that little bit nearer to the speed of light. In fact, the bottom line is that to reach the speed of light, you've got to provide something with infinite energy. That's what Einstein's special relativity theory says, and it's been proven many times. So if you put infinite energy in, then you've hit the speed of light, but you haven't got infinite energy. That's what we're talking about, an absolute maximum for the temperature. So the maximum temperature is infinity. That's what it means. So there isn't one. There is an absolute zero, but not an absolute maximum. There you go. Yeah, that's the bottom line. There's a little bit more to it because relativity also tells you that as things approach the speed of light, their mass increases, and that's why you need to put more energy into to get them going any faster because their mass has gone up. So it's never going to happen. You're always going to be able to add more heat to it to increase the temperature, even though the particles might be traveling very near the speed of light. They're not actually there.
Yeah, you start off throwing a screwed up piece of paper, and as you get there, you're trying to push a planet.
Yes, that's right. That's it. That's exactly right.
Yeah. All right. Thank you, Tom. I think we've got time for one more quick one. This is a fun question from Rennie. It's a what if question. Rennie asks, if plants and animals were discovered on another planet that we landed on, would we be able to digest its plants and animals? I assume he means, could we, feed ourselves? That's so. Yeah, I suppose if it was a planet like ours, maybe, I don't know, but
yeah, and if we had water-based living organisms, which the plants and animals would be, they might be similar enough to what we have on Earth that we could digest them, but I think it might be a bit difficult. And would you want to be the guinea pig? Pick up a piece of meat from some random planet somewhere?
Yeah.
So thanks. My guess is that it will be unlikely. There might be trace elements that would be toxic to us. Even if it was a water-based life form, there could be stuff in it that you really would not want to bother with.
Notwithstanding the bacteria and virus impact that we would never have been able to defend ourselves against.
Yes,
there'd be all sorts of reasons not to. Yeah. So possible yes, logical no. Maybe it's the best way to answer it. Thanks, Rennie. Great question. I love the hypotheticals. Just one more thing before we finish up, Fred. I got a lovely message from Hannah, the airline pilot, the other day. Hannah introduced herself to us some years ago when she sent us photograph from the cockpit of her British Airways airliner of noctilucent clouds. She's just sent me some more photos, which I've shared on the Space Nuts podcast group Facebook page. She's done a time lapse of the supermoon rise above a volcano
lovely.
in South America on her way to visit Alma. So, I'm so jealous. They're great photos. And especially that moonrise she took. She was trying to do it handheld, so it's a bit wobbly, but it's worth looking at. And yes, that is a big volcano right next to the moon. So it's amazing. And so getting to see the Alma Observatory, what a great opportunity for her. So thanks for sharing those, Hannah, and you can check those out on our Space Nuts podcast group Facebook page. There you go. We're all done, Fred. Thanks for answering those questions.
It's a pleasure, Andrew. Thank you very much for asking them. And,
no, my pleasure indeed. Oh, a late message from TTJ. Hi, boys. I started to listen to all the episodes from the start after hearing one of the new episodes first. I'm now up to episode 76. Still got years worth before I catch up. Thank you both. Thanks for finding us. We appreciate it. Tell your friends. Fred, until next time, au revoir.
Au revoir and auf Wiedersehen.
Yeah, and goodbye.
Yes.
And as we say in this country, see you later.
See you later, mate.
Yeah, mate. All right. See you, Fred. Fred
right.
Watts, an astronomer at large, and thanks to Hugh in the studio for sending us all those last-second questions live and in person. Well, no, he's not here. I've actually never seen the guy. And from me, Andrew Dunkley, thank you again for joining us. Thanks for sending in questions. And don't forget to go to our website so you can send more, spacenuts.io. Until next time, take care, and we'll see you real soon on another episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.